In this video lecture, we will be discussing two more examples which is related to the symmetry. So as we discussed in the previous video lectures that what is a symmetry, and we also discussed its two types. There are two types of symmetries basically. The one is the vertical symmetry and the other one is the horizontal symmetry. And we also discussed the set of rules which we use for the vertical symmetry and for the horizontal symmetry. Now in this video lecture we will be discussing two more examples which is related to the horizontal and the vertical symmetry, in which the first one is related to the vertical symmetry. So basically in this example we are asked to find out the equivalent resistance between point A and point B. So first of all, if we draw a horizontal line which can join these 2 points, point A and B. Now if you look into this network and if you want to find out the horizontal symmetry in this circuit, so you can see that there is no mirror image present of the upper side at the bottom, or there is no mirror image present of the bottom side on the upper side. So we can say that there is no horizontal symmetry exist in this network. So now we will be looking for the vertical symmetry in this network. So if we draw a vertical line which bisects this horizontal line with 90 degrees by 90 degrees, so you can see that there exists the mirror image of this side on this side. So we can say that this A point is the mirror image of this B point, and these resistors are the mirror image of these resistors. So by the rules of the vertical symmetry, we know that the current will be the same on either side of the symmetry. So now if we assume if there is a current I which is entering to this network, so now there are two choices for the current to flow through these two resistors. The one path is this one and the other path is this one. So let's say the current through this path is I1 and the current through this path is I2. So by the rules of symmetry we can say that if there is current I1 through this resistor, then the same current will be through this resistor, because this resistor is the mirror image of this resistor. So there will be the current I1 through this resistor also. So at this node here we have again two choices for the current I2 to flow through these two paths. So the current through this path is, let's say, I3. And the current through this path is, let's say, I4. So according to the rules of vertical symmetry, the current through this resistor will be the same as the current through this resistor, because this resistor is the mirror image of this resistor. So the current I through will also be flowing through this resistor. And this current I4 will also be flowing through this resistor, because this resistor is the mirror image of this resistor. So we can say that there exists the current I4 through this resistor also. And the current through this resistor will be I2, because this resistor is the mirror image of this resistor. So we can say that the current I2 will also be flowing through this resistor. So now at the end there will be the current I through this point, because there is current I which is entering at this A point. So this A point is the mirror image of this B point. So the current I will be exist through this B point also. So as you can see there, these two resistors are connected in series, because there exists a same current through these two resistors, and these two resistors are connected also in series, because there exists the same current through these two resistors, because this current I3 at this node will follow only this path, and this current I3 is not following this path and this path. So these two resistors are in series. And this current I1 is also flowing through this resistor and not following these two paths. So these two resistors are in series. Now for the simplification purposes, if this point is point C and this is point represent point D. Now let's redraw the simplified version of this problem or this complex circuit. So let's say this point represent the point A and this point represent point B, and this point represent this point C, and this point represent the point D. So now in between A and B, these two resistors are connected in series, because there exists the same current through these two resistors. So these two resistors are connected in series. because there exists the same current through these two resistors, which is the current I1. Now in between point A and C we have another resistor R. Between point A and C we have another resistor R, and there exists the current I2 through this resistor. Now in between point C and D, these two resistors are connected in series because there exists the same current through these two resistors. So in between point C and D we have two resistors which is connected in series, and the current I3 is flowing through these two resistors. Now in between point C and D we have two more resistors which are connected also in series because there exists the same current through these two resistors. So in between point C and D we have two more resistors which is connected in series, and there exists the current I4 through these two resistors. Now in between point D and B we have another resistor which is R, and there exists a current I2 through this resistor. So now this is the simplified version of this problem. Now let's solve this network by using the rules of series circuits and parallel circuits. So if you look into this network, then you will see that these two resistors and these two resistors and these two resistors are in series. So now the equivalent resistance of these two resistors is, let's say, R dash is equals to R plus R, which is equals to 2R. And the equivalent resistance of these two resistors will also be 2R, and the equivalent resistance of these two resistors will also be 2R. Now let's replace these two resistors, and these two resistors by its equivalent resistance, which is 2R. Its equivalent resistance of 2R, 2R, and 2R. Now if you look again into this network, then you will see that these two resistors are in parallel, because these two resistors are sharing the same 2 points. So the equivalent resistance of these two resistors is, let's say, 1 divided by R double dash is equals to 1 divided by 2R plus 1 divided by 2R. So R double dash from this equation will be equals to R. So now let's replace these two resistors by its equivalent resistance, so we can redraw this network again to obtain its simplified version. So the equivalent of these two resistors is R. So if you look again into this network, then you will see that these three resistors are connected in series. So the equivalent of these three resistors is, let's say, R triple dash is equals to R plus R, which is equals to 3 into R. So now let's replace these three resistors by its equivalent resistance. Its equivalent resistance of 3R. Now if you look again into this network, then you will see that these two resistors are in parallel because these two resistors are sharing the same 2 points. So the equivalent resistance between point A and B will be equals to, let's say, 1 divided by RAB is the equivalent resistance, which is equals to 1 divided by 2R plus 1 divided by 3R. Now RAB from this equation will be equals to 6 divided by 5 into R. So this is basically the equivalent resistance between point A and B, and we find this equivalent resistance by using the rules of vertical symmetry. So it's all for the vertical symmetry. Now let's move towards another example which is related to the horizontal symmetry, in which we are asked to find out the equivalent resistance between point A and B. Now let's use the rules of horizontal symmetry to find out the equivalent resistance between point A and B. Now let's first look into this network. Is there exist any horizontal symmetry in this network? So let's redraw a horizontal line which join these 2 points A and B. So now if you look into this network, then you will see that the upper side is the mirror image of this lower side because the same resistors are connected at both the sides with the same resistance value. Now let's use the rules of horizontal symmetry, which states that the voltage will be the same on both the sides of the horizontal symmetry. So now let's say the voltage at this point is A, and the voltage at this point is X, and the voltage at this point is Y, and the voltage at this point is B. Now the voltage at this point is X, so the voltage at this point will also be X, and the voltage at this point will also be Y, because there exists the horizontal symmetry in this network. So if there exists a horizontal symmetry, then at the symmetrical points the voltage will be the same. So this point is the mirror image of this point, and this point is the mirror image of this point. So we can say that the voltage at this point will be the same as this, and the voltage at this point will be the same as this point. And as the potential or the voltage is the same as at this point and this point, so there is no potential difference across this resistor. So we can say that there is no current through this resistor. So we can remove this resistor to simplify our analysis. So let's redraw this network again. So let's say if this point is point A, and this point is this point X, and this point represent this point Y, and this point represent this point B. So if you look again into this network, between point A and X we have a resistor R. Between point A and X we have resistor R, and between point A and X we have another resistor which is R. Another resistor which is R, because the potential at this point is the same as the potential at this point. So we can connect these two resistors to this same point. Now between point X and Y we have this resistor, and between point X and Y we have another resistor R. So between point X and Y we have resistor R, and between point X and Y we have another resistor R. Now between point Y and B we have two resistors also connected, which is the first one is this one and the second one is this one. So between point Y and B we have this resistor which is R, and between point Y and B we have another resistor which is R, and this is point B and this is point A. So now by using the rules of series circuits and parallel circuits we can find out the equivalent resistance between point A and point B. So if you look into this network, then you will see that these two resistors are in parallel, these two resistors are in parallel, and these two resistors are in parallel, because each of these resistors are sharing the same 2 points. So the equivalent resistance of these two resistors are, let's say, 1 divided by R dash is equals to 1 divided by R plus 1 divided by R. So R dash from this equation will be equals to R divided by 2. So the equivalent of these two resistors is R divided by 2, and the same is the case for these two resistors and for these two resistors. So now let's replace these two resistors, these two resistors, and these two resistors by its equivalent resistance. So let's say this point is point A. Now let's replace these two resistors by its equivalent resistance, which is R divided by 2, and this is point X. This resistance is R divided by 2, the equivalent of these two resistors, and the equivalent of these two resistors is, let's say, this one, which is R divided by 2, and this is point Y, and the equivalent of these two resistors is R divided by 2 also, and this is point B. Now if you look into this network again, then you will see that these three resistors are in series. So the equivalent resistance of these three resistors is RAB, let's say, equals to R divided by 2 plus R divided by 2 plus R divided by 2. So the equivalent resistance of these three resistors will be 3 divided by 2 into R. So the equivalent resistance between point A and B, the equivalent resistance between point A and B is equals to 3 divided by 2 into R. So this is basically the equivalent resistance between point A and B, and we find the equivalent resistance between point A and B by using the rules of horizontal symmetry. So it's all for today's presentation. If you have any doubt, ask in the comment section. See you in the next one.